Hello, welcome everyone. I am member one from Group I, and today we are presenting our virtual machine and assembly language interpreter for the object-oriented programming and data structure subject. We will take you on a quick code walkthrough, and where each member will explain a specific layer and a structural role in the virtual machine, and I will be explaining layer 1, the foundation of our project, because the project strictly forbids us from using STL libraries such as std, vectors, stacks, queue, and so on. We built our Actually, we built our own custom data structure using C++ templates and dynamic memory management. Let's break through our first vector, our first class, myVector. First, we implemented a custom dynamic array template to mimic a standard vector. Actually, it tracks the capacity and the size and utilize a resize function that automatically double our capacity when it's full, ensuring that no memory leaks occur during our reallocation. Moving to our next class, myStack. Actually, we created a custom stack to manage the hardware 8-byte system, and if a pop operation is attempted on an empty stack, as we can see here in the if statement, if the top index is less than or equals 0, you will see this message right here, system crash, stack underflow, and the program triggers an immediate system crash to simulate a hardware underflow as required in the specifications. Finally, let's move to our last class in our first layer, myQueue. Actually, we implemented a sequential first in, first out queue to buffer the incoming text instruction first from the assembly file, ensuring they are executed in the correct order. And now I'm gonna pass the mic to member 2 to explain how we utilize these structures to build the hardware.
Thank you. I'm Shaoxi and I will be covering layer 2, the core hardware state engine. This layer strongly demonstrates the OOP concepts of encapsulation, composition, and inheritance. Firstly, we have registers. We created a base register class representing a single byte and derived general register from it to represent our 8 general purpose registers R0 to R7. All values are private and strictly processed via public getters and setters to maintain encapsulation. Next, we have flags and memory. We implemented a flag register class to manage the carry. To manage the carry, zero, overflow, and underflow flags. And a memory class to represent the 64-byte RAM, complete with boundary checks to drop invalid memory addresses. And lastly, we have the CPU. The CPU class ties this all together through strict composition. The CPU fully owns its memory, myStack, general registers, and flag register. A key feature here is the update arithmetic flags method, which simulate unsigned math behind the scenes to accurately calculate the carry flag. While checking standard thresholds for overflow and underflow. Alright, the next member will explain how we handle the assembly instructions dynamically.
Hello, professor. My name is Amir Garbi. Today, I will show you layer 3 of our group project, which use inheritance and polymorphism handle how our instruction work. First, we have in structure here, as we see, class at the top. This is our abstraction parent class, and it's act as a blueprint. The virtual destructor, this line, is very important because it's clean up the memory properly when an object is deleted and preventing any memory leaks. The execute function, as we see here, this is a pure virtual function. It is empty here, but it sets a strict rule that forces every specific instruction we create later to have its own execution logic. Moving on to the move instruction class, okay, which handle all the move comments. Inside its execute, as we see here, execute function, we use a simple if-else blocks to move data using three different modes. Mode 1, as we see here, moves a direct number into a register. Mode 2 copies data from one register to another register, as we see here. And mode 3 handle indirect memory, where it read data from a RAM address using CPU read mem. At the very end, it checks here. It checks the result and update the CPU zero flag automatically. Now, moving on to the next main class, the arithmetic instruction class. This class is for math operation like add, sub, INC, and DEC, as we see here. This class have some work to do. First of all, constructed overloading. I built two constructions here, one handle register to register math, and the other handle directly numbers. This keeps our code very clean. Second, inside its execute, as we see here, function, it automatically gets the correct value, perform the math calculation, and saves the final answer back into register. And finally, right after that, it calls CPU update arithmetic, as we see here, which tells our core hardware engine to update all the complex flags like carry, overflow, and underflow for us. In conclusion, this polymorphism design makes the code modular and very easy to expand. That is all for layer 3. Thank you so much for your time.
Hello, I'm Ziantu. Today I'm going to present the layer 4 interrupter engine. So this layer is an orchestrator that reads the files and drives the CPU. Now let's start. So let's go to main. Everything starts here. So in main, we load the file, run it, and dump the result. Load file. So in the runner class, we load ASM file line by line, queuing them up, and we also implemented strict checks to throw an error if multiple instructions occupy a single line. So decode instruction. So the decoder processes the text, strips out bracket and commas, and instantiates the correct dynamic instruction objects into our custom MyVector. So this one, the run part. The run loop steps through the Veda using the program counter executing instruction polymorphically. So finally, once the program finished, we call the demonstrate functions. So we ensure the output perfectly matches the required format using the delimiter to map out begin, registers, flags, PC, and memory. Yeah, and exactly as shown in the project specification. So guaranteeing full compatibility with automated gradient. So conclusion. So as the conclusion, this conclude the architectural breakdown of our virtual machine. So all while maintaining clean code under the 35 line limit per function. So thank you so much, and this is all for our presentation.